Well, getting the hang of Kirchoff's laws and how we analyze a circuit that way can take a little getting used to, so I thought I'd make another video that might help you. This one is a little more concrete. I'm going to actually work with numbers. I'm going to go all the way to the final answer, which might make this go a little bit long, but you can skip the parts maybe that you already know, or maybe something I'd recommend is if you are just practicing this a little bit, you could stop the video and see if you can finish certain parts yourself. What's tough about this is there's different ways to set up the problem, even though there's only one solution. So I'll be telling you as I go through this where I'm making choices that you might make different choices. And actually, the very beginning is a place where you might make a different choice than I do. We first have to decide how many different currents we could even measure in a circuit such as this. So if you look what I have here, there's 3 different what we call branches, places where we could measure current. And they're separated by these locations that we call junctions. So what new students sometimes do is they think we'll have one current here along the bottom, maybe up to the point where I get to this resistor, and then I have a different current in this part, and then maybe even a third current up here around the corner. But you just have to know that when current flows through a branch like this, it doesn't get used up, it doesn't get created in any part of the circuit, it's just traveling through there like water through a hose. So if we go in one part of a resistor, we're coming out the other part with the same amount of current. So I'm going to assign a couple of currents. I'm going to use names that kind of make sense based on the resistors they're going through. And the arbitrary part to this is, first of all, what you name them, but second of all, how you draw them in a certain direction. There's no way that we would know at the beginning of a problem which way the current is supposed to go. So I'm going to kind of randomly pick here that in this branch here on the left, I'm going to imagine current going in somewhat of a counterclockwise fashion. And I'm going to name this after the resistors that it flows through. So that's I-23 because it flows through a 2 ohm and a 3 ohm resistor. Now just note that that's between this junction and this junction here. It does not include anything here. That's a different amount of current. So I'm going to name a current going this way between those junctions along that branch I4. I've drawn it up somewhat randomly. You could draw yours down, but we'll get slightly different looking work as part of this. And then I'm going to draw a clockwise current here in the rightmost branch, again, just between the junctions, and I will call that I5 because it flows through a 5 ohm resistor. So there are the currents that I want to name, and now the next thing we need to do is to describe how those currents would relate to each other. This is what we refer to as a junction equation. So at the point on those junctions where the currents are going in or coming out, we cannot create new current at a junction. We cannot make current disappear at a junction. So we set up a junction equation that basically says all the current going in is equal to all the current coming out. It doesn't matter which of the 2 junctions you choose, you're going to get basically the same equation. So at this top junction here, we have one current going in, that's I4, and we have 2 currents going out, that's I23 and I5. So the total in and the total out have to be identical. So that is one of the 3 equations that I'm going to use to describe how these currents relate. Now, the other 2 equations, I think I'll do this in a different color, maybe green. They are called loop equations. They are independent of the junction equations, although they do contain the same unknown variables, I23, 4, and 5. So the loop equations are going around a complete round-trip path. So I've got this loop here on the left, I've got a loop here on the right, and I've got a loop around the entire perimeter. I think just for a little variety, I'm going to write one loop equation for here on the left, and I'll write one around the entire thing just to show you that I can do that. So I think I'm going to start here in the lower left corner, and I'm going to make a path clockwise all the way around like this. And you see why I chose a different color. I don't want to get it confused with my current directions. So I would certainly encourage you to maybe use some color yourself. So this is the left loop equation. And if you choose to go in a counterclockwise direction, you're going to get the same terms, but every sign will be opposite. So every plus will be a minus, every minus will be a plus. So what we write for the loop equations is potential drops or potential jumps. So every time we go through something that would tend to read a lower potential, we call that a drop, and we call it a negative delta V. Every time we go through something that would jump in potential, we call that a jump, and we write that as just a plus delta V. So every time you run into something is when you're going to get a potential change. So heading this way, clockwise, the first thing I run into is this resistor that has current running through it. Now notice the current is running downward. The way I drew this current, the red arrow is pointed downward, but I'm going in the other direction. So that means the way I've got this drawn, I would have a higher potential at the top part of this resistor than I would have at the bottom. That's if the current is flowing in that direction, which remember, I never knew going into this whether it was or not. I'm just imagining that that's what it could be. When it all is said and done here, I may find that I'm going to get a negative sign on my answer. That just tells me I chose the wrong direction, and you'll see that happen when I get to the end. So this would be a jump as I'm going through it here. And the jump, when you go through a resistor, is equal to the current multiplied by the resistance it's going through. So in this case, it's I-23 multiplied by 2 ohms. So that's my first jump. Now, I travel around some wires some more, and then I get to this battery. Notice which way I'm going across the battery, from the low potential to the high potential. That's also a jump. In this case, a jump of 12 volts. And now I'm going to go down this way. Notice I'm going against the current. I go through this battery here from the plus to the minus now. So that's a drop of 15 volts. These drops here and jumps around the batteries have nothing to do with current. So I'm just looking for whether I go from the high potential or to the low or from the low to the high. But now because I'm going through this resistor, again, opposite the way I drew current I4, that would also be a jump. So this would be a plus I4 times 4 ohms. And continuing on, I make the turn here. I'm going to go, again, opposite the direction I drew the current. So that's a jump of I-23 times 3. And now that I'm back to where I started, that lower left-hand corner, this is where I say all the jumps and all the drops cannot have made me change my potential. This is really ultimately an energy conservation equation. I can't have changed the energy if I'm back at the same spot. So that means the sum of all my potential changes must be 0. So I just finished up my equation there with equals 0. All right, I need another loop equation. This time I think I'll write in blue. I'm going to go start in the lower right-hand corner this way, and I'm going to go counterclockwise this time. So I'll go up this route here, write the same kind of expressions that I wrote before. So I'll say this is my whole loop. Again, you get the same equation no matter where you start. It just depends on what order your terms are written in. So I'm going to head up this way. I run into this 5 ohm resistor that has current going opposite the direction I'm moving through it. So this would be a jump of I5 times 5 ohms. Then I'm going through a battery in the way that batteries are intended to be used. So that is a plus 20. I was looking at the other battery. Plus 20 volts. And then I go here through kind of the wrong direction in the battery. So that's minus 12 volts. Now notice I'm going through the 2 ohm resistor in the direction that I had drawn the current originally. This is I-23 I'm talking about. So I had drawn it downward through here. So now I have a minus I-23 times 2 ohms. We get minuses when the direction that we're moving through our loop matches the direction that we drew the current. And then in a similar way, going through the 3 ohm resistor, that's also a minus I-23 times 3. And then I continue on, I get back to where I started, and I don't run into anything else. So I say that's equal to 0 as well. So here are 3 independent equations that show the relationship between I-23, I-4, and I-5. Now my next step, just to organize things, and of course at this point, the physics is done. You could stop here and say it's now a math problem. You know, go find yourself a math major somewhere and hire them to solve this problem for you. If you have a really good calculator, you have a solver on there, and it lets you put in as many independent equations as you want to, hit the solve button, and it tells you what all your unknowns are. You might call them X, Y, and Z instead of I-23 and things like that, but it's still just solving a system of equations. I'm going to show you a matrix method because that's the way I've gotten comfortable doing it. It's certainly not the only way to do it. Some teachers don't even teach about matrices anymore, but I at least want to show you a scheme for doing this. So the first thing I do is I rewrite each equation so that my variables are all in the same order. I'm going to use 23 and then 4 and then 5. And I want them all on one side of the equation. So when I rewrite my junction equation, excuse me, I would write I-23 minus I-4 plus I-5 equals 0. And that's exactly the same equation I had before, just written in a slightly different order. And then my left loop equation, see, I have two terms with I-23 in it. So I combine those together, and I get, I'm going to leave the ohms off for now. I'm going to say this is 5 times I-23. That takes care of this and this. And then here's one term that has I-4 in it. So that's plus 4 I-4. And then I don't have any terms with I-5 in it. So I'm going to write plus 0 I-5. That's a little unusual. You wouldn't do that in a math class. But because I'm organizing a matrix, I want it to be that way. And then what's left here? I have 12 minus 15, which is negative 3. But I want to bring this over to the right side of the equation, on the other side where I have after my equals sign. So I'm going to call that a positive 3. That would be 3 volts. Okay? And then I'm going to write my whole loop equation very similarly. Again, I have two terms with I-23 in it. They're both negative, so this is minus 5 I-23. I want to make sure you can see this. I have no terms at all with I-4 in it, so that's plus 0 I-4. And then I have one term with an I-5 in it, so that's plus 5 I-5. And then what's left are these two, which is 20 minus 12, or negative 8. So moving that over to the other side, algebraically, I have a positive 8 over there. And I just did that wrong. You notice I have 20 minus 12. That's negative 8, or positive 8. And so moving it over makes it negative 8. Just caught my mistake. I had actually worked this through ahead of time, so I was able to catch myself. So now I have what math teachers would call a system of equations, and here it is. So I'm going to now write this as a matrix equation. If you haven't done a matrix before, I'm not sure this is the best time to learn, but I'll show you what it looks like, and you can decide if you like it or not. A matrix basically says, if I have a system of equations, you cluster the one side of the equation into a 3 by 3 matrix. This is just the way I do it. You don't have to do it this way. A 3 by 3 matrix where your matrix is made up of the coefficients of each of your unknowns, but they have to be in the same order. So that's why I clustered them in this order here. So my coefficients are 1, negative 1, and 1 in this first equation. My coefficients in the same order in the second equation are 5, 4, and 0. And in the third equation, it's negative 5, 0, 5. So all those, and then if we multiply that by a matrix that includes our unknowns, I-23, I-4, and I-5, basically that times that, it's got to equal the answers to these. This is on the other side of the equation. That's our 0, 3, and negative 8. So what you're going to see here on the screen, I'm actually recording over verbally because when I made this recording, I inadvertently left the negative off of the 8 in that second matrix. And all you have to do is make one little mistake on a matrix like that, and it completely changes the answers. So I'm flipping through here to show you what I did as far as keystrokes on my TI-83 calculator. And I doubt many of you would be using a TI-83, but at least shows kind of what the output looks like. So the solution to this are the three currents that I'm looking for. And what you see on the screen are my mistake answers that I'm just going to tell you what to replace them with. So the first current we were looking for was called I-23, and it comes out actually to positive 0.72. The second current should be a negative 0.15, and the third current a negative 0.88. Now I want to highlight those second two there, the negative 0.15 and the negative 0.88. Those are negative because my original scheme of setting up currents, which I did at the very beginning of the video, and I drew I-23 and I-4 and I-5. But now that I have a negative sign in my solution, all it means is my original choice of the direction was opposite of what it should have been. And that's not that I made a mistake, it's that I just legitimately did not know what the correct directions were. But you see, you don't have to know what the correct directions are going into the problem, because by the time you're all done, you will have figured out what the correct directions should be. Okay, so again, just ignore the final numbers that I throw there, and what I'm doing here is explaining exactly what those negative signs mean. So you got the same description here with this little overdub. So hopefully this wasn't too awkward as a way to try to fix my mistake. I do want to thank Alex, who's a student in my class this year, for doing his own calculation of this as he practiced for his test, and came up to me and pointed out my mistake. So I'll give him credit for actually this correction. So, all right, I think that's going to do it for here. Hopefully, working through the matrix process helps you a little bit better with solving a Kirchoff's law problem. Good luck with all the ones that you're going to be doing.